Hello everyone, welcome back. So today we are continuing our tree series, and as I mentioned in our last video that we are going to cover binary tree and binary search tree in detail and its definition, application and types for both we are going to cover today. So let's first start for the binary tree. So by definition you can say that a binary tree is a hierarchical data structure with at most two nodes. This word at most is most important. And if you remember, the most important property that I told for binary tree is that each node can have one incoming and two outgoing branches at max. So at max is important because there can be less or there can be more. And I have written that if there is no incoming branch, then it is a root node. And if there are no outgoing branches, then it is a leaf node. And rest are all are intermediate nodes. So remember these 2 points very, very well. With definition, we are done. So one of the most important application of binary tree is basically used in its uses we can mention in representing arithmetic expressions. So what is an arithmetic expression? Um, let's take the example 5 plus 4 into 3 minus 2. This is an arithmetic expression. So when you represent this in a binary tree, there are two rules that you have to follow. First rule says all operands must be leaf nodes. And second says all operators must be intermediate or root nodes. So if we have to solve this expression that I have written here with a tree, what we can do is we can say it is something like 5. So it should be a leaf node. And then it must be connected to an intermediate node, which would be plus, and then there would be another expression. Let's call that expression as T1. So in our, if I use a different color, in our example, this entire expression from here to here, we can represent it as T1. So let me draw that expression here. 4 is an leaf node, multiply is an intermediate node, 3 is again a leaf node. And then we can say that minus is again a intermediate node and 2 is a leaf node. And if you want to replace this part here, so what I can do is I can remove this T1 from here and can just simply take this part from here and put it here. And there is no need for this arrow now. How easily we can represent an arithmetic expression using a binary tree. right? So the board mass rule you do not have to follow. Your level will decide whether which expression should be solved first. So that's what we did here. Multiply was having higher precedence, so we first used it, and then at the top the lower precedent operators came. So after this, let's move towards the third part where we say what are different types of binary tree. There are a lot, and we will go one by one along with the definitions. There is something called a full binary tree. So a full binary tree means every node has either 0 or 2 children. So at the right side, I will try to draw one, and as I keep on explaining the types, I will keep on making the changes in the tree. So suppose this is a tree. This is a full binary tree because each node are having either 0 or 2 children. Second point, the second type is a complete binary tree, which means all levels are filled except last, which must be filled from left. So this one, the image that you are seeing is not a complete binary tree because this level here, this part, this is not filled. Only the last level, this part here, this can remain empty. But here, this part is also empty. So it is not a complete binary tree. To make it a complete binary tree, we have to do this. Now all levels are filled. This level is filled, this level is filled, and this level is also filled. But the last one, this one, and is filled from the left side. And you can say that this is also a full binary tree because it is satisfying the property of either both the childs are present or no child is present. But if I remove this node, now this is still a complete binary tree, but it is not a full binary tree because the leftmost part here, this is having a single child, not 0 or 2. Okay. So I will make it complete again. Third one says perfect binary tree. It says all nodes having have 2 children and all levels are filled. So to make it as a perfect binary tree, we have to fill the last level. Now this is a perfect binary tree. It is also a complete binary tree. It is also a full binary tree. And the fourth one we can see is skewed. A skewed binary tree is one where only one node is filled at each level. So if I need to convert this to a, so I have to make sure that only one node is present in the entire structure. I have to remove this entirely because I have used it. So this one should be removed entirely. And there can be more like this. So this is a skewed one. It is not representing any hierarchy or something. It's kind of a linear structure, data structure that we are having. So this one is, you can say, is the worst case. If your tree is something like this, that means you are you're not effectively using the tree to store your data. Either your data is not present in such a manner that you can represent it as a tree, then you have to think of some different data structure, or you are not filling it correctly, because this is not solving any purpose. This is not going to help you in any manner. And this what we are going to see when we learn more about binary search tree. Then you will understand why a skewed tree is useless, is totally useless. So yeah, this is the worst case. So I will just make the tree again. Okay. So that's all about binary tree. Now we will move to very important topic, binary search tree. In short, it is called a BST, binary search tree. Now the property of binary tree still holds, that each node can have at max one incoming and two outgoing branches. That property still holds because it is a binary tree only. The term search is important, and that means is the term search comes with a another property, another definition, and that says the left node should be less than the root node, which should be less than the right node for all sub trees. Now let's understand this definition with an example, because this is the most important property. So let's see, we have a tree here. I'll keep the property visible so that you can see that. Let's say this is our tree. Okay. It is not a full binary tree, it is not a complete binary tree, it is not a perfect binary tree, but it is still a tree. Okay. Now, see carefully how I am filling the values. I have not filled these arbitrarily. There is a logic behind it. Now, to understand the logic, at each node, just apply this property that I have written here. If you see from at 30 point, suppose your eye is right now here. If you see from here, see what all nodes are present at the left hand side. They must be less than 30. And which all are present at the right hand side, they must be greater than 30. I have also mentioned another point, that this should hold for all subtrees, which means that if I shift my eye from this to this point, now for this tree which starts from 50, all left nodes should be smaller and right node should be greater. The other part of the tree, this is not at all visible from 50. That is only visible from 30. So that's why this is the property of a binary search tree. And why we called search, I mean, this is a property of greater than or less than, then why I'm saying that it is a search tree? Because it effectively searches the element inside it. So if I just remove this I from here, I will make it place it back at the root. Suppose you have to search 55. Our target is 55. There are total number of 11 nodes that are present in the tree. So if you have to search 55 in 11 nodes, at max you are going to take 11 steps or 11 iterations, right? When you have to search something. But in a binary search tree, due to this property, see how effectively you can search in lesser number of steps. So whenever I is at 30 and we have to search 55, we know by this definition that 55 cannot be present in this tree. It cannot be present here. It is not possible that it is present because it is greater than 30. So what we can say that we can effectively remove this tree from our main tree. We can ignore this totally. Now, when we shift our eye to the next point, here we can see that 55 is still greater. So what we can do is we can very effectively remove this part also. We can ignore that. No need for it. Now when we again move our eye to the next part, we know that 55 is less than 60. So we can ignore this point. Now let's move to another one. Here we are able to get our answer. How many max number of steps or iterations we did? We move 1 here, then 2, and then 3. That's all. In only 3 steps, we were able to find our answer. Otherwise, in case of a linear structure, this would have taken 11 iterations or 11 steps. That is why it is called a binary search tree, because it can effectively search anything, right? And that search is the at max is the height of the tree. And height of a binary tree, you can say at max is log to the base 2 of n, where n is the number of nodes. That is why if you have seen somewhere or you have heard what is the time complexity of searching is in a binary tree, it is considered log n, represented as big O of n. I hope you got this. I have made this a bit clutter. I cannot stitch it again. So I will just remove all these parts. But I hope the things are clear. Now, the applications or uses for a BST are many. As we just saw, it is used in searching. It can be used in sorting. And one more application is it keeps the data in sorted order. Well, you might ask how it is keeping in sorted order because I have written the numbers here and there. You can also say that, okay, we understand how searching is done, but you still cannot see the data in sorted order. But let me tell you, in upcoming videos, when we will be learning about pre-order, in order, and post-order traversals of the tree, we will see how the data we can extract from the tree in sorted order. So these are few of the applications. Searching is the most important one. Sorting is also used, and the sorting of the data part is also very helpful. And this is also mentioned in the last video about the self-balancing trees. There are two types, AVL and RBT. RBT stands for red black tree. It is implemented in C++, STL, map, and set classes. These topics are advanced and comparatively bigger. So I will devote an entirely new single video to each of these topics on AVL and RBT. But let's first understand what is a self-balancing tree. So if you remember, one type of binary tree that we mentioned is the skewed binary tree. Something like this. And I mentioned this is the worst case. a skewed tree, worst case, because it is not making any help to us, right? It is not keeping the data in any hierarchy. Everything appears to be linear. And from the binary search perspective, now you can say if you want to search something, then it is going to take the linear time. You have to traverse entire node. It is not possible that you can ignore the entire one part of the tree and you can search effectively if you just recall the example that we just take. So a skewed tree is useless. So what self-balancing trees does, by some mechanism, and we are going to cover that later, but here we are, I'm just giving you a dummy example of that it will convert a skewed tree into a complete binary tree. So that we can effectively uses the properties of a binary tree or a binary search tree. Otherwise, a skewed tree is not giving us any benefit. So that is the use of self-balancing trees, right? Apart from this, heap is another type, and we have seen about the heap. It has a lot of applications, priority queue and all that we already covered. So with this, I think we are at the end of our today's lecture as well. So two things we covered: binary tree we covered, and then binary search tree we covered. In our upcoming lecture, we are going to learn about pre-order, in-order, and post-order traversals of a binary tree or binary search tree. With this, I would thank you for watching. If you have any questions, please let me know in the comments below, and see you again. Bye.